Now that we have learned what a tree is like, let's discuss binary trees. A binary tree is a regular tree in which the number of children of any node is limited to at most 2. So you can have nodes with 0 children, which would be the leaf nodes, 1 child or 2 children, but not more. This is an example of a binary tree where, again, in the figure, these small empty squares are showing the null pointer. So the root S has 2 children, P and O. P has only 1 child, I, and there's no right child. It has only 1 child here. And similarly, O has 1 child, which is N, but it doesn't have the other child. S and M have no children, so they're examples of leaf nodes. So we will need 2 different data structures for this. One would be for the external nodes, and the other for the internal nodes here. So let's focus on what we call a complete binary tree. A complete binary tree is a binary tree. So again, a node cannot have more than 2 children, but with the term complete, we mean if the tree has, say, n levels, in each level, all possible node positions are filled with a node. So every level, in other words, is full. So in this example, we have a complete binary tree with 4 levels from level 0 to level 3. So we have the root node, then its 2 children, then their 2 children, and it goes this way. Now, if you look at the number of nodes in this complete binary tree, in level 0, we have only the root node, which is the normal case. The root should be unique. In the next level, since we have the whole level full, we have 2 nodes, then 4, then 8. So as you can see, the nodes are getting doubled in every level, which is normal because instead of this parent node, you get 2 children, and this repeats for all. So if the total number of nodes would be 2 to the 0 in level 0, 2 to the 1 in level 1, 2 to the 2, and 2 to the 3. So we know the sum is equal to 2 to the 4 minus 1, which is 15. So in other words, for a complete binary tree with 4 levels, you would have 2 to the 4 minus 1 nodes at most. So if we try to define this in more generic terms, let n be the number of nodes in the tree, and let m be the number of levels. So the number of nodes would be 1 plus 2 plus 2 to the 2 plus 2 to the 3. So it's 2 to the 0 plus 2 to the 1 plus 2 to the 2, going all the way to 2 to the m minus 1, where m is, remember, the number of levels, because we start the enumeration from level 0. So this summation we know is, in general, 2 to the m minus 1. So 2 to the m is equal to, take this minus 1 to the other side, equal to n plus 1. If you take log base 2 of both sides, m would be equal to log base 2 of n plus 1. Remember, in this course, when we say log, we mean log base 2. So if we have n nodes in a complete binary tree, then the number of levels would be log of n plus 1. Remember, n was the number of levels, which is, in general, big O of log n, because log n would be equal to log n plus 1 when we're talking about big O. Or equivalently, instead of the number of nodes, if we're given the number of levels, then we can find how many nodes we can store in that tree, and that would be 2 to the m minus 1, as we know. And if you take the big O of this minus 1 you can get rid of, so it is big O of 2 to the m. These are important results, because this tells us, the second one tells us, if you can afford to have m levels in the tree, you can store at most 2 to the m elements. And the first one says, if you have n elements in the tree, if you're talking about a binary tree, the best you can get for the number of levels would be log n. Now, why do we care so much about the number of levels? The number of levels is important because when we're looking at the tree, we will decide to go left or right. Remember, in the tree, we need to decide whether we should go left or right. And that would require a comparison, as we will soon see here. So whatever the number of levels is, we will have to make so many comparisons. So the number of levels is very important because it determines the maximum number of comparisons we need to make to find what we're searching for. And therefore, we would like to have a small number of levels. In other words, try to fill the binary tree as much as possible to try to have a balanced binary tree. We will be discussing this in more detail in the following sections. So, how can we represent this? Remember the strange representation we had earlier. We had the pointer to the first child, and then that child had pointers to its next sibling, and this way we had the linked list. Instead of that, since in the case of binary tree, the number of children is limited. It's 0, 1, or 2, not a large number. I can afford to have 2 pointers, one for the left child, one for the right child, and one field for the element itself, the data to be stored in that node. That would be sufficient for me. So in other words, this time I have direct pointers from the parent to the child. Note that we don't have reverse links from the child to the parent, but having 2 pointers would be sufficient. And what if you don't have 2 children but you have 1? Make the other one null. You would be wasting 1 pointer, but that's not a big deal. If you have no children for the leaf nodes, then both of the links would be null.